applications for this, that it's helpful to see that it's kind of useful. I will also admit I have tried. I've been searching the internet for like really like applicable related rates problems. There are several of these that I'm going to give you that are going to feel like they're very like contrived problems, like a math teacher made this up and nobody in the real world was ever going to do it. I have looked for a lot of other like really useful, helpful problems that real people do. One of the issues I have ran into is a lot of the applications of these things are for like higher level science sort of stuff, and I don't know the science well enough to like really explain what's going on there. So one of the reasons we're doing these kind of like problems that don't seem like they're as applicable is because the ones that are too hard for us right now. Like I tried to, and I found a few that I'm going to throw in that I think are very helpful. So some of these you might be like asking yourself, why would you do this? You know, and I think some of them are just like to get the process of being able to do it. Some of them, you got to go a little further before it comes like really, really applicable. But I like this problem because it makes sense to me, kind of like why you would need to know this. So a police officer is parked 30 feet away from a straight road. He uses his radar gun to find the speed of a car driving down the road as shown in the picture. Now, I am not an expert on police radar, and they probably have something better that like accounts for this, possibly. But we're going to assume that they're just using like a little radar gun like you use for like baseballs or something like that. In which case, what this police officer is finding is really the speed at which the car is moving away from him, not the speed at which the car is moving down the road. Those two things are not the same. So it tells us at the time the car is 100 feet away from the police officer, and the radar gun reads 70 miles per hour, which is about 103 feet per second, which is important because we got to have our units match. At what speed is the car traveling down the road? Whenever we look at this problem, you can see I've got like A, B, and C labeled. And this should be a right triangle. So if it is a right triangle, we know that A squared plus B squared equals C squared. Now, when we do a problem like this, we have to think about what is changing. Like calculus is the math of dynamic things, things that are changing. So we need to know if things are changing or not changing. So is there anything, like if we look at the values of A, B, and C, is there one of those that is not changing? It is A. The police car is not moving yet. It's just sitting on the side of the road, hidden behind a bridge or something, looking for a speeder, trying to get them. So A is not changing. It's constant. So since A is constant, we can go ahead and plug it into the equation. So we've got, was it 30? Yes, 30 feet away. So this is 30 over here. So we've got 30 squared plus B squared equals C squared. And so in a related rates problem, what we do is we take the derivative of this function, but we take it with respect to time, because everything is relative to time. The car is traveling at so many miles per hour, right? So how long the car has been going down the road deals with how long B or C is. So everything is with respect to time. Time is not always that extra variable, but it usually is. So we've kind of done something similar to this before whenever we did like implicit differentiation, and we took the derivative with respect to x. So if we had any y's, we had to put a dy dx with it, right? So like that would be like when we had x squared plus y squared equals 25. We'd have 2x plus 2y, and that y we'd have to put the dy dx with it because it didn't match. So when we're taking the derivative with respect to time, none of the variables match the t, right? So we will take the derivative, and everything is going to have that extra dB dt or dc dt or whatever with it. Now, the derivative of 30 squared is just 0 because it's a constant number. So that's going to be 0. It's going to go away. The derivative of b squared is 2b. But because that b is not a t, and that's what we're taking the derivative with respect to, we have to put dB dt with it. And for our c squared, our derivative is 2c, and we have to put a dc dt with it. Now, B and C are still the lengths of the sides of those that triangle. What you don't really know about yet is what dB and dC even stand for, what they mean. dB dt is the rate of change of B. So when we see that dB dt there, it's our rate of change of B, and dC dt is our rate of change of C. So the problem gives us some things that we can plug into our equation here, and then we'll be able to solve for something. So as we read through the problem, it says, yes, at that time, so this is like one instant in time, right? Both B and C are changing, so this is only at this one instant of time. The car is 100 feet away from the police officer. What variable is that going to be? C. So we know at this time, C equals 100. And the radar gun reads 70 miles per hour, but because 100 is in feet, we really want to use 103 for our feet per second. What would that be? It is dC dt. It is the rate of change of C, because this radar gun is reading the speed that distance is changing between the police officer and the car. So dC dt at this moment is 103. And again, we want to use the feet per second instead of miles per hour because our scenario is in feet here. Now, if we look at this equation right here, we can plug those things in. So 100 will go right here for the C. dC dt will go here to 103. What is the question wanting to know? It says, at what speed is the car traveling down the road? What would that be? That's dB dt. That's what we're looking for. So we need to solve for dB dt. So we don't want to replace dB dt with anything because that's what we're going to be solving for. What are we missing? B. Could we find B? We could, because this is just Pythagorean theorem right here, right? So if C is 100, right here, we could go over here to the side, and we could say 30 squared plus B squared equals 100 squared. So that's 900 plus B squared equals 10,000. So B squared would be like 9,100. We would square root both sides. B is the square root of 9,100. So we can take that and plug it in right here. So then we have a pretty simple equation to solve, because we're going to have 2 times square root of 9,100 dB dt equals 2 times 100 times 103. And to solve for dB dt, we'll just need to divide by 2 square root of 9,100 . If I want to, I could cancel those 2's right there to make it easier, and we're going to reach for our calculator here because that's not going to be an easy number. So and I didn't hit the green button. I'm getting 107.973. And that would be in feet per second. So the radar said the car was going 103 feet per second. But according to these calculations, it really should be about 108. This is working in the driver's favor, because it is, the actual speed's higher than what the officer is saying they were going anyway. So it wouldn't really be an issue in this case. Let's change that to miles per hour to see how much different it is. So if I do 107.973 feet per second, if you remember back from like chemistry converting units, if seconds are on bottom, seconds need to be on top here, and we're changing that to hours. How many seconds are in an hour? 3,600, 60 times 60. So 3,600. So that would like cancel the seconds there. So now you change that to hours. Then you need to do feet are on top, so you need to put feet on bottom, and you want to change that to miles. How many feet are in 1 mile? 5,280 here. So if we were to multiply, and that would cancel your feet with feet, so now you'd have miles per hour. So if we multiply that number right there by 3,600 over 5,280, we're going to get 73.6182. You don't. You do not necessarily have to, because it didn't specify. So, and pretty much you're probably not going to see like an AP question where you've got to convert miles to hour, feet per second. They usually don't have you do anything like that for the problem. I just like converting it back to miles per hour because like that, I can picture something going 73 miles an hour. When you go feet per second, I don't have that pictured in my mind. Okay. So you can see it's only like 3.5 miles per hour difference in the speed, but there is a difference. So I definitely could see like a scenario where this might be important to know here. Now, again, I'm not an expert on police radar. They may have something like built into the system to account for that, possibly. I don't know. But I do know this is like sort of how it works. If it is built into the system to account for this, something inside of the computer that's running all of that, that's telling the police officer the speed, is making these sort of calculations somewhere, possibly. For that. So, I just thought that's kind of like a a kind of neat example to look at to see where something like this would apply. There are going to be all kinds of things that we look at. We're going to look at some different like area and volume problems. There's all kinds of triangle problems that we'll look at. And there's a lot of like applications in like science and business and things like that. We'll look at a little bit of those, although that's really where you start getting into, this is probably where it's most useful, but we're also just not like, we don't know enough to really look at those situations. The problems get too hard for that. Now, that is the only, oh no, I might have one application at the end. Did I leave that here? Yeah, I did. I got one more application at the end just to kind of get a little practice, but your homework is going to look like 2, 3, and 4 tonight. So just like what I would call a naked problem, no context whatsoever. So it says, given y equals x squared plus 3, find dy dt when x equals 1 if dx dt equals 2 when x equals 1. Okay, so whenever you see a problem like this, what you want to notice is that this dy dt, dx dt stuff. So this is not dy dx, which is just like a regular derivative like we normally take. You've got that dt in the bottom of it, which means the derivative was taken with respect to t. So we would need to take the derivative of this function with respect to t. In cases like this, it's really simple. It's like doing implicit differentiation, except for everything gets a dy dt or a dx dt, depending on what the variable is when you take the derivative. So like for y, you would have just dy dt. And then you'll take the derivative of x squared. It's going to be 2x. And you put a dx dt with it. And then you got the plus 3. The derivative of that is just 0, so it goes away. And then, so once you've taken this derivative, most of the time, all you've got to do from here is plug in the pieces of information that they gave you. So they told you that x equals 1. Why is it lagging? There we go. X equals 1. So right there for x, we're going to replace that with 1. It tells you that when x equals 1, dx dt equals 2. So dx dt equals 2. That is going to go right here. And then it was asking us to find dy dt, which is this over here. All right, so that plugs everything in that we need. So it'll look like this. We got dy dt equals 2 times 1 times 2, which will give us 4. So dy dt equals 4. Now, something important to know for these problems, and when we get to more applications, we'll look at this more in depth, but dy dt is not always 4. Dy dt equals 4 in this scenario when x equals 1 and dx dt equals 2. All right, so it's only for this scenario. If we change the value of x, then dx dt might change. We don't know. They didn't tell us what it was. And then our numbers would be different. So in most of these situations, what you have is not like a constant rate of change. You have these rates of change are changing. So you're only looking at like one specific scenario for this. But the general process, take your derivative with respect to t, plug in, solve is what you're going to be doing for this. Now, let's do one that's a little bit tougher. We've got x squared plus y squared equals 16. What's that equation of? What shape is it going to be? Circle. Is a circle, what's the radius? Not 16. Not 8. 4. It's the square root of 16 because it's x squared plus y squared equals radius squared for that. So that was just a bonus see what you remembered. You don't need to know it for this. So we'll do the same thing we did on the last problem. Take your derivative. So you'll have 2x dx dt plus 2y dy dt equals 0. And then it's asking us to find dx dt. So dx dt is what we're looking for. We're not going to replace it with anything. X equals 4. So that goes over here for our x. And it tells us dy dt is 3. So that goes right here. Now this one is a little bit like the one that we just did. Do we have anything else that we're missing? We're missing that y, right? We need to know what that y is. So since we don't, because we can't solve for dx dt while we still also have a y there, so we need to see if we could figure out what the y is. What could we do to find y? Plug 4 into the original. Perfect. So over to the side, I'm going to say 4 squared plus y squared equals 16. So 16 plus y squared equals 16. You may already be seeing what the answer is going to be here, because those cancel out. Y squared equals 0, so y equals 0. So we'll take that and plug it in right here. So we've got 2 times 4 dx dt plus 2 times 0 times 3 equals 0. I don't love the answer to this, but that's what happens. You've got 8 dx dt plus 0 equals 0. So really I don't even have to write that plus 0 if I don't want to. So how do I solve that? Divide 8. What do I get for my answer? 0. I don't like it, but it is the answer. So dx dt equals 0. Again, this is when x equals 4. In this case, it's not for every point on that graph, but at x equals 4. Dx dt equals 0. I would. These are usually not given as FRQs. If they're just like a naked problem like this, they are usually given as multiple choice. So it would usually not be an issue. They would not include it in the answer on a multiple choice because they've asked you this question. It says when this happens, what is dx dt, so it wouldn't be necessary. If you did see it on an FRQ, I'd put it there, but I think it's highly unlikely you'll see it as an FRQ for that. Okay, questions? All right, let's do one more that's harder. Okay, so again, it's the same process every time. What gets more difficult about it is the equation you're dealing with is more difficult. So this itself doesn't have any like extra steps that are super hard, but taking the derivative of this equation is harder than the first ones that we did. And the main reason is because of this first part. What do I have to use to take that derivative? Product rule. And like, I wonder if you call this implicit differentiation whenever you have dt. When I say implicit differentiation, I usually mean like dy dx. But I wonder if this technically is like a branch of implicit differentiation. I'll have to look that up. I don't know. Yeah. So, but this has to have product rule. So we'll have 2x times the derivative of y, which is dy dt. And we know we're doing dy dt because it's asking us to find dy dt. So we have to take the derivative with respect to t. Plus, and then we'll have y times 2, but with that we have to put dx dt. So that takes care of our product rule part at the beginning. Then we also have this y squared, so that's going to be 2y dy dt equals the derivative of 8x is just 8, but it has a dx dt. Most of the time, I do not try to simplify anything for this. I don't try to solve it for something. I don't try to put things together because usually once you plug the numbers in, it'll be easier to deal with after that. So I usually just leave it. I would change this and make it 2y instead. But can I put 2y dx dt and 2y dy dt together? Cannot. The variable parts are not exactly the same. So I'm just going to leave it like it is. I've got y equals 1. I've got dx dt. I'm trying to solve for dy dt, so I don't want to replace this. Much like the other problem, what is left that I need to find? We want to find dy dt, that's what we're solving for. What other variable are we going to have to find in order to do that? The x, because it gives me y, it gives me dx dt, but I don't have the x. So if I want to find the x, I got to go back to the original problem, plug in 1 for y. So I'm going to do 2x times 1 plus 1 squared equals 8x. So that gives me 2x plus 1 equals 8x. We'll subtract that 2x there. 1 will equal 6x. And we'll divide by 6. So x equals 1/6. And so now we just need to plug everything in. So I've got 2 times 1/6. I don't know dy dt, that's what I'm solving for. And then y, which is 1, times 2 times the x dt, which is 5, plus 2 times 1. I leave dy dt because that's what I'm solving for, equals 8. And then dx dt is 5. And now you're just solving this equation. It does have some fractions in it, but it's still just like a linear equation to solve. So this will be 1/3 dy dt plus 10 plus 2 dy dt equals 40. So I could subtract that 10 right there. And then I could put these two right here together. I've got to do 2 plus 1/3, which you got to do common denominators to put those together. Multiply that by 3 on top and bottom to do 6/3 plus 1/3 is going to give you 7/3. So I've got 7/3 dy dt equals 30. And then you're going to divide by 7/3. But I like to, on this, dividing fractions is easy as pie, flip the second and multiply. I like to just go ahead and multiply by the reciprocal. If you multiply by 3/7 here, you'll get dy dt equals 90 over 7. And of course, this is when y equals 1. Okay. All of your homework is going to look like this. Naked problems, no context. You're just working through. You're going to take the derivative with respect to t. You're going to plug in whatever information they've given you. Sometimes you have to go back to the original to get that other variable, solve for, and then solve for your final answer for that. Now, I do want to do one more application problem. Now, this is really one of those that math teachers have just made up. Maybe there's a scenario where this happens. In a rectangle, the length is 8 feet longer than the width. The length of the rectangle is changing. When L equals 5 feet, the L dt equals 5 feet per second. Find the rate at which the area is changing when L equals 5 feet. So this is, you could you could change this to be more of an actual real problem, but this is pretty contrived here. But you got to start somewhere whenever you're doing these problems. So we've got a rectangle, and the length is 8 feet longer than the width. So in our rectangle, we got length and width, and we know that the length is 8 feet longer than the width, so the width plus 8 right here. All right, so the question is asking us to find the rate at which the area is changing. All right, so if it's asking me about the rate that the area is changing, the formula I need to start with is area of a rectangle. Right, so I would say area equals length times width. Now, you may not want to write this next part down. Here is the problem if I take the derivative of this equation, right? And again, we'll go over this even more later. I'm just trying to get you a little bit introduced to it. If I take the derivative of this with respect to t, I got dA dt. That's what I'm trying to solve for, right? Because it's the rate that the area is changing. That's going to be my dA dt. It's going to equal L times dW dt plus W times dL dt. Now, if we start looking at trying to find what we're doing here, this is what we're solving for, right? Because the rate at which the area is changing, that is dA dt. That's what we're solving for. I know L is 5, so I know that. I can plug that in. I could find W. That's not an issue. I know dL dt is also 5, so I can replace that. Again, I said I could find W because it's just, 8 less than this. What about that dW dt? Do I have any information about that? I have none, right? I don't know anything about dW dt. I also have no way of figuring out what dW dt is. There's not any way that I could do that. So, while everything I did here is correct, you wouldn't be able to solve the problem if you did it this way. So sometimes you have to backtrack, and you have to look at your original equation. So I've got A equals L times W. Which rate do we know? We know dL dt. So if everything was L's, then I'd be able to do this problem, right? And I can do that because I've got L equals W plus 8. So if I just subtract that 8 from both sides, then L minus 8 equals W. And I could replace that right here. So A would equal L times L minus 8. And this you want to write down because this is the direction we're going to go. And I'm going to go ahead and distribute that L to get L squared minus 8L. Now, when I take the derivative of this, there will be no dw dt, so this will work. So if I take the derivative here, I'll get dA dt equals 2L dL dt minus 8 dL dt. Everybody good here? So now we're just plugging in. We don't have to worry about what W is because it's gone. Now it's not part of our problem. We know L is 5 and dL dt is 5. So dA dt is going to equal 2 times 5 times dL dt is 5 minus 8 times 5. And we are going to get 50 minus 40, and we will get 10 for that. Now, these are usually going to need units with them. So, this is dA dt. So, that top thing is area, and the bottom thing is time. And in this case, we were measuring the length in feet. So what would area be measured in? Square feet. Very good. And then time for this problem was seconds. So it'll be feet squared per second. So the area would be increasing at a rate of 10 square feet per second. At that moment. This would be when L equals 5 feet. Here. Now, I do not necessarily expect you to be able to do number 1 or number 5 again on your own necessarily at this point. We're going to look at it more in the other sections of notes. I just wanted to include a little bit of that here. Your assignment for tonight is going to be from page 194. You're going to do 1 through 4 and 5 through 8, but in 5 through 8, it asks you to do, like there's an A, B, part A, B, and C or something like that, where you basically just have to work the same problem over again 3 times. So only do the part A part of that just because it's like extra workload for that. So we've got lots of time. Hopefully you'll be able to get this done before you go. And then you'll have time to work on your FRQs, maybe tonight, because I will say that homework for tomorrow and the notes for tomorrow are a little tougher.